Hello and welcome to video number 2 in this series of tutorial videos for HDXmodeller, and in this video we're going to go through a summary of the various different validation methods that are used by the algorithm. So before we begin, I thought that it might be instructive if I give some details on how HDXmodeller was developed. So the algorithm was actually benchmarked against synthetic data, so this is an approach based on so-called ground truth, which is different to say gold standards. There's merits for either method, and it's beyond the scope to go through that in these videos. So first of all, a crystal structure was taken for any protein, and protection factors, or the natural log of the protection factor, LNP, were then simulated according to this expression here. This is Micheli-Vendruscolo's famous phenomenological expression, and if you want the reference for that, you can find it in our communications biology paper. So once the LNP values have been simulated, then these were then used to build HDX-MS data using an experimental peptide map for that protein. And so here we have an example of this showing the RFU, or the relative fractional uptake, which is kind of a normalized deuterium incorporation for 80 different peptides. You can do this over any number of different time points. In this example we have seven labeling time points, and so this was then taken as an input for optimization, and the performance of the algorithm was then measured on, or based on, the level of correspondence between the optimized LNP and the inputted simulated, or the original simulated LNP values. There's some missing data here. This is just because it's an experimental peptide map, and we didn't have full coverage. So importantly, the performance of the algorithm was also appraised based on its ability to assess its own performance, and this was done using a novel approach based on a covariance matrix, which generates this term that we call the R matrix, and we're going to look at that in a short while. So to understand the validation method, the main validation method, I think that it's probably best if we start by looking at a failed optimization. So in this plot here we have reference and also optimized LNP, so natural log of the protection factor, for a protein, and these data were generated as previously shown. And obviously you can see that there's extremely poor correspondence throughout the data here, and actually the correspondence is variable. It's better in some regions than it is in others. If we overlay the experimental peptide map on top of these data, and also look at the redundancy, this can be quite informative. In this case, obviously in these regions here, there are too few peptides to constrain the data properly, and you shouldn't really expect good optimization outcomes for these regions here. And in general, we recommend that weak peptides, which are poorly constrained peptides, are deleted prior to optimization. And we actually have a tool that can help you identify these papers, an occupier tool, which can be found for this URL here. So what we also notice is obviously the performance of the optimization is variable throughout the data, and so we thought that it might be best to split the data into different subsections, as shown here. There's 4 different subsections: a black one, a red one, a blue one, and a green one, and then optimize each of these subsections independently. So these are the 4 different subsections as shown here, and when these are optimized independently, as expected, we get different performance, optimization performance, as shown by the respective coefficients of determination here, which is the correspondence between the optimized LNP and the original reference LNP. So obviously it's very easy to gauge accuracy when you have access to the true reference values. But in the real world we don't have this, of course, so that posed the question, how can the accuracy of optimization be quantified when we don't actually have any knowledge of what the true values are? And so for this we developed a novel method. This is, I should also say, this is actually a general problem with optimization in, you know, any kind of optimization method is how can you ascribe confidence to the outputs. And when we started looking at this, we began by looking at the experimental data. Obviously redundancy is often taken as a good indicator of how well a data set's going to optimize, but aside from redundancy having to be above a certain threshold, it's really quite a poor indicator. So you can see that from these two data sets. Obviously the subsection in green has many more peptides and therefore a higher redundancy, and yet the coefficient of determination is much lower than the one that we get from optimization of the blue subsection. So we developed a method based on a covariance matrix, and this is an example covariance matrix from an optimization that involved 100 different replicates. So each of these pixels here shows the correlation coefficient, so R, between any two replicates, and from this we determine this value called the R matrix, which is simply the arithmetic mean of all these different R values. And to benchmark this, we generated a library of 30 different subsections of data, so as shown on the first slide there, subjected all of these to optimization, and then this could generate a library of these correlation matrices as shown here. And this plot here shows the relationship between the R reference, so this is the actual accuracy of the optimization, versus the R matrix, and this is how well modeler thinks it's performed, so how accurate it believes the accuracy to be. And you can see that there's a very high correspondence between the two, so HDXmodeller is able to appraise its own performance with an accuracy of 99%. And so this is a general method that we think should be followed for any optimization with HDXmodeller to separate data into different subsections, analyze them independently, and then ascribe confidence or use the R matrix values to help you ascribe confidence to the optimization outputs for each subsection. So there are various different validation outputs. Obviously the R matrix one is the main one, and as previously mentioned, we recommend that data are first split into different subsections. Each subsection is then submitted for optimization separately, and then the R matrix score is inspected as a measure of the overall accuracy of that subsection. The really neat thing about this is that because these R matrix values are determined post optimization, this actually enables a sandbox approach. So you can users can use different optimization strategies with the same data set, such as using a different loss function, for example, and then inspect the R matrix outcomes from the two separate optimizations and choose the one with the higher score. Other optimization outputs include the optimization histograms. This is residue level information. It's difficult to ascribe too much to this. Normally the median is a good representation of the true value, and so, you know, a broad histogram such as this doesn't mean that the optimization is poor, but on the other hand, greater confidence can be ascribed if you get a very narrow distribution such as the one shown here. We also have a weaker validation output on the residue level, which is the R matrix score, and this is simply the change in the R matrix when each amino acid is deleted in turn from the calculation. Magnitude should not be interpreted as simply the direction of the delta R matrix, and more confidence can be ascribed to residues that yield a positive score than those that yield a negative score. We also have some tools, statistical methods, which can analyze the consistency of data in terms of peptide error, and you should inspect our analytical chemistry paper from 2021 for more information on that, and here are the references below. So I hope that video has been useful. Thanks for watching, and I'll see you in video 3.